Okay, number 7, in corn kernels. Kernel color is governed by a dominant allele for white, capital W, and by a recessive allele, lowercase w. A random sample of 100 kernels from a population in Hardy-Weinberg equilibrium reveals that 9 kernels are yellow or homozygous recessive and 91 kernels are white. Now, you should be familiar now that because it gave us the number of homozygous recessive individuals, we can easily calculate Q squared. But it also gives you how many white kernels. And here's why we're not going to use that number for anything right now. To be a white kernel, obviously you have to have the dominant allele present. So that could be big W, but there's another way to get that as well, and that is big W, little w. So do not try to use that number to start calculating anything. It is really difficult to calculate P squared initially. It's easy to do Q squared because there's only one way that you can be recessive, and that's if both alleles are present. So that's just something to be mindful of when you start to see these problems in real life. So we're going to start with that homozygous recessive percentage first, that Q squared. So to find the Q squared, well, first I'm jumping the gun here. Let me get to what the question is. It wants us to calculate the frequency of the yellow and white alleles. And then it wants us to calculate the percent of this population that is heterozygous. So it wants us to calculate P and Q. Those are our dominant and recessive alleles. And then it wants us to get the heterozygous percentage, or 2PQ. So let's go ahead and get part A out of the way. So Q squared is, again, they tell us that there are 9 yellow kernels. 9 is not Q squared. Q squared has to be the number of homozygous recessive individuals divided by the total population. So that is going to be 9 divided by our total population was 100. So our number for Q squared is going to be 0.09. That is not the end. We need Q. Q is the square root of 0.09, and that is going to be equal to 0.30. So Q out of the way is 0.3. So we got our first answer. Now I got to calculate P. P plus Q is 1. So 1 minus 0.3 is going to be 0.7. So P is going to be equal to 0.7. That's out of the way. Now calculate the percentage of the population that is heterozygous. That's 2PQ. So 2 times P, which is 0.7, Q, which is 0.3. Do the math, you get 0.42. Percentage-wise, 42% of this population is going to be heterozygous. So pretty straightforward for this one. Number 8, a rare disease which is due to a recessive allele that is lethal when homozygous occurs within a specific population at a frequency of 1 in a million. How many individuals in a town, with a population of 14,000 can be expected to carry this allele? Okay. Always start with the homozygous recessive percentage. So in order to have this specific lethal disease, you have to be homozygous recessive. And it tells you this occurs in about 1 in a million. So Q squared is literally 1 in a million. So we have to get that number, which is 0.000001234. Is that 5? 1, 2, 3, 4, 5, 1. There's Q squared. Now to calculate Q, we got to take the square root of it. So Q is going to be 0.001. That is the frequency of allele little a. Okay. Now, it wants to know in the question, so let me get my highlighter out. how many individuals in a town of 14,000 can be expected to be a carrier? Carrier, not not unaffected, not affected because they're dead, a carrier. This is 2PQ. It wants to know about being heterozygous. It doesn't want to know the percentage of individuals in this town of 14,000. It wants to know, if I were to count them, how many, what number are expected to be heterozygous. So let's find some more information. We've got Q here at 0.001. Now we got to find P. So again, P plus Q equal to 1. We've got Q, so we do 1 minus 0.001. That's going to give us 0.999. That is our P. So now we can calculate 2PQ. We are going to go ahead and just add an additional step. So 2PQ is 2. Let's not add the additional step because let's do it all at once. To calculate the number of individuals, I need to do 2PQ times the number in the population. So we're going to do 2P was 0.999, Q was 0.001, and then we got to multiply that by 14,000. So that is how many people are in this population. We're going to get 27.97. We'll go ahead and round that to 28. So 28 people should be carriers in this population. 28 people. Okay, so now let's go to questions 9 and 10. They refer to the same situation. 2 Siamese and 3 Persian cats survive a shipwreck and are carried on driftwood to a previously uninhabited tropical island. All 5 cats have normal ears, but one carries the recessive allele or folded ears. His genotype is big F, little f. Calculate the frequency of alleles, big F and little f, in the population. And then, if you assume Hardy-Weinberg equilibrium for these alleles, about how many cats would you expect to have folded ears when the population reaches 20,000? Okay, so for number 9, it wants to know Q and it wants to know F. So let's go ahead and get number 9 going. Now we are told that the genotype to be a carrier is big F, little f. So the 4 other cats are not carriers, so their genotype for that trait is big F, big F. So 4 cats are big F, or they are that P squared number. There are 10 total alleles within this population. So in order to find the frequency for our allele, we're going to have to do 9 over 10. It's 0.9. So that is our P number. And to find our Q number, we're going to have to do 1 over 10, which is going to be 0.10. Now, if you assume this population is at Hardy-Weinberg, how many cats can be expected to have folded ears once this population reaches 20,000? So to have folded ears, you have to be little f, which is Q squared. So Q squared is going to be equal to 0.10 squared. So that's going to be 0.010. And the number of cats with folded ears would have to be the total population multiplied by Q squared. So when I get that, it's going to be 20,000 times 0.010. So that's 200 cats. 200 cats will have folded ears. In a certain African population, 4% of this population is born with sickle cell anemia. little a, our Q squared. Calculate the percentage of individuals who enjoy the selective advantage of the sickle cell gene, increased resistance to malaria. So we are going to be calculating 2PQ today. Okay, so the individuals that are heterozygous, they have a selective advantage. So they have increased resistance to malaria. So they're carriers of the trait. They do not have the full-blown sickle cell anemia disease. They're going to be represented by 2PQ because that is our heterozygous term. We were told that 4% of the population is affected with sickle cell. That's our Q squared number. So Q squared is equal to 4% or 0.04 when expressed. So in order to find Q, we have to take the square root of 0.04. It's going to be 0.20. So we got Q squared, we've got Q, got to calculate P. P plus Q equals 1. So 1 minus 0.2 is going to be 0.8. So that is our P. Now we got to calculate our 2PQ. So 2 P is 0.8. Q is 0.2. Do the math and we get 0.32 or 32% have that selective advantage or are carriers. All right, in the United States, approximately 1 child in 10,000 is born with PKU, a syndrome that affects individuals that are homozygous for the recessive allele. This is a 3-part. We're going to calculate the frequency of this allele in the population. We're going to calculate the frequency of the normal allele and calculate the number of carriers. So the frequency of the allele, we need to calculate the frequency of having that PKU. So we are finding Q. We're going to calculate the normal allele, that's P. So Q is our recessive allele. P is our dominant allele. And 2PQ will be our carrier, our heterozygous allele. 2PQ is heterozygous. Okay, so let's start with part A. It tells us that 1 in 10,000 kids are born with PKU. So Q squared is going to be, Q squared is the number of homozygous recessive divided by the total population. So we're going to get our number by doing 1 out of 10,000. That is going to be equal to 0.0001. So that's Q squared. So all I've done is calculate the frequency of being homozygous recessive. They just want to know the allele. So Q is going to be equal to square root of 0.0001. Q is therefore, when I do the math, 0.01. Next, I have to calculate the frequency of the normal allele. Well, I just got the frequency of the allele that affects the population. So all I have to do is P plus Q equals 1. So 1 minus 0.01, and that leaves me with 0.99 as my frequency of having the normal allele. Lastly, we're going to do the percentage of carriers with the trait. So to find the carriers, we're going to do 2PQ. So it's 2 times 0.01, 0.99, and I get 0.0198. So that is going to be multiplied by 10,000 to obtain the number of heterozygous carriers. So I can take that 0.0198, multiply it by the population of 10,000, and I can figure out that 198 people in this population are carriers of the trait. So I'll just box all of this in. Okay, so now let's do a Hardy-Weinberg mixed in with a chi-square analysis. So, in Caucasian humans, hair straightness or curliness is thought to be governed by a single pair of alleles showing partial dominance. Individuals with straight hair are homozygous for the IS allele, while those with curly hair are homozygous for the IC allele. Individuals with wavy hair are heterozygous ISIC. In a population of 1,000 individuals, 245 have straight hair, 362 have wavy hair, 393 have curly hair. So what we're going to do is calculate the allelic frequencies of the IS and IC alleles. The straight, the wavy, the curly, and the total. So it told us that so we're going to start with this number of IS alleles. So we're going to start with straight. So straight hair, 245. So in order to be straight hair, you have to be IS. So we're going to take 245, multiply it by 2. That's going to be 490 IS alleles. Now we're going to calculate the wavy hair. Be wavy, you are heterozygous, or ISIC. So 362. Now we got to calculate the curly ICIC, and we're going to leave that at 0. Now we're going to calculate the number of IC alleles. Okay, so over here, we have 0 IC alleles if you are ISIS. In order to be wavy, you still have 362. And in order to be curly, you have to be 393 times 2, which is going to be 786. So let me just go over real quick where these numbers came from. IS alleles is the first thing that I looked for. To be straight, you have 2 IS alleles. So that's why I multiplied it by 2. In order to be wavy, you just have 1 copy. So that's why the number stayed the same. To be curly, you don't have any. So that's why it's 0. When I went over here to do the IC alleles, let me do a different color. To be straight, you don't have it. So that's why it's 0. To be wavy, you just have 1 copy. So that's why it stayed the same. To be curly, you have 2 of them. So that's why we multiplied it by 2 to get that number. So let me do a different color again. So let's calculate the total. So the P is going to be 852 divided by 2,000. And that is going to be equal to 0.43. Q is going to be 1,148 divided by 2,000. It's going to be equal to 0.57. So far, so good. Now, is this population at Hardy-Weinberg equilibrium? Justify your answer. Your explanation should include a chi-square goodness of fit test. Okay, so let's start with our straight, our expected, our wavy, all of these little things that we love so much about chi-square analysis. So let's start over here with the observed straight. Okay, we observed of the straight allele, we observed, let me see, I gotta read again. We observed 245 from our problem. We expected to have 185. So for our Q squared, have to be 0.43 squared times 1,000 equals 185. When I do the O minus E, it's going to be negative 60. Wavy should be expected 400, no, our observed was 362. Our expected for wavy was 2PQ times the population number. So 2, 0.43, 0.57, 1,000. It's going to be 490. So when we get our observed minus, sorry, this should have, I don't know why it doesn't have a little section for observed minus expected. It's fine, we can calculate it out later. Now let's go over to curly. We expected for curly to have 393. Our expected curly is, well, this should be p squared up here. Should be q squared. It's going to be 0.57 squared times 1,000 equals 325. So then we get our totals, blah, blah, blah. So I'm going to have to do a lot of stuff off camera like I did. So I'm going to write out the entire chi-square analysis. You can sit here and go through the chart like you've practiced, but I'm just so used to doing it freehand that I'm just going to write it out. So 60 squared over 185 plus negative 128 squared over 490, and then plus 68 squared over 325. Once I do the whole chi-square analysis, I get 67.1. Our degrees of freedom, as always, is going to be n minus 1. So 3 minus 1 is 2. And we always use the 0.05. So 2 degrees of freedom. My critical value is 5.99. So here, 5.99. And my chi-square, so this is my chi-square up here, is 67.1. So it looks like something really crazy is happening. So my hypothesis was that Hardy-Weinberg was occurring. There was Hardy-Weinberg equilibrium. However, my chi-square value was 67.1, which is far, far bigger than 5.99, which was my critical p-value. So we're going to reject the hypothesis that Hardy-Weinberg equilibrium is occurring. We are going to conclude that Hardy-Weinberg equilibrium is not occurring in this population because my critical value or number is higher, or I'm sorry, is lower than my chi-square. Thus, evolution is occurring. Okay, as always, if you have any questions, please feel free to email me. I look forward to hearing from you. Have a great day.